Hello everyone! In this video we're going to go over the KutaSoftware Infinite PreAlgebra free worksheet similar figure word problems. I'll leave a link in the description below so you know how to access this free worksheet provided by the KutaSoftware website. Now our directions for numbers 1 through 8 are to answer each question and round your answer to the nearest whole number. So if we're starting with number 1, it says a 6-foot tall tent standing next to a cardboard box casts a 9-foot shadow. If the cardboard box casts a shadow that is 6 feet long, then how tall is it? So I think the best thing here to help us visualize this is to actually draw a picture. So what I like to do is I like to go through my problem and underline important information as I draw my picture. So we have a 6-foot tall tent. So here I'll just put my tent, and it is 6 feet tall. Next to a cardboard box. So I'm going to draw a little cardboard box down here, and that is, well, remember, we're trying to figure out how tall that is. So this cardboard box is what our unknown is. Now it says that that tent casts a 9-foot shadow. So we have some shadow that the tent casts that is 9 feet long. And we know that the cardboard box casts a shadow that is 6 feet long. And using this, you can kind of see our proportion already. 6 is to this unknown measurement, the height is to that unknown measurement, as the length of the shadow is to the other length of the shadow. Or we could do 6 feet to 9 feet is proportional to our unknown to 6 feet. Just remember, just like similar figures problem, we just need to keep our numerators and our denominators in line. We can either keep them within the same figure together, or we can keep the same type of sides together. So in this case, let's keep our figure together. So I'm going to have 6 feet, which is how high the tent is, over the length of its shadow, which is 9 feet. And that's going to be equal to the height of the box, which is our unknown. I'm going to write that as our variable x, over 6 feet, that side. Now it's just a one-step equation. So I'll multiply both sides by 6 feet to solve for our unknown height x. 6 feet and 6 feet will cancel out on my right-hand side, and 6 times 6 is 36 feet. So I'll have 36 feet over 9 feet is equal to x. And remember that label, we have it in feet. 36 divided by 9 is 4. So we know that 4 feet is our solution for how tall the cardboard box is. So this is 4 feet. If we wanted to set up our proportion another way, really quickly, I'll do it right here on the side. We could have done how tall our box was, x, over how tall the tent was, 6, and that would be equal to the length of the box shadow, 6, over that 9. Either way, we're going to get the same exact solution. Let's move on to number 2. For number 2, we have that a telephone booth that is 8 feet tall casts a shadow that is 4 feet long. So let's go ahead, draw this telephone booth. We know that its height is 8 feet, and it casts a shadow that is 4 feet long. Find the height of a lawn ornament that casts a 2-foot shadow. So we have some lawn ornament here. We don't know its height, but we do know that it casts a 2-foot long shadow. Well, let's set up our proportions. 8 feet is to 4 feet, as our unknown length is to 2 feet. Or I could say 8 feet is to our unknown length, as 4 feet is to 2 feet. There's multiple different ways to set up this proportion. Let's put our unknown side over 8 feet. So I'm going to label that unknown side as some variable x. X is our unknown. Over 8 feet is going to be equivalent to, if I put my unknown side over 8, I need to put my shadow length of that unknown side, which is 2 feet, over the shadow length of the telephone booth, which is 4 feet. And I know that x is going to be in feet, since all my measurements are in feet for this problem. So this is just simply a one-step equation. We're going to multiply both sides by 8 feet. And when we do so, 8 feet cancels out with 8 feet on the left to leave me with x equal to 2 times 8 is 16, and 16 divided by 4 is going to be, again, 4 feet. So we have that the lawn ornament is 4 feet tall. Let's move on to our next problem. For number 3, it says that a map has a scale of 3 centimeters to 18 kilometers. So we're doing a little bit of mixed measurements here, but let's just keep them in order. If Riverside and Smithville are 54 kilometers apart, then how far apart are they on the map itself? So if our scale is 3 to 18, and that's 3 centimeters to 18 kilometers, I'll write 3 centimeters over 18 kilometers. We need to know how far apart they are, Riverside and Smithville, on some map. So we're looking for that centimeter distance between them. So let's make this variable x. And that's going to be all over our 54 kilometers because that's how far apart they are actually. Again, one-step equation, we're going to multiply by 54 kilometers to both sides. What this does is it gets rid of this 54 kilometers in our denominator because 54 divided by 54 is just 1, and 1 times x is x. So we're going to have 54 times 3 over 18, and 18 actually goes into 54 evenly 3 times. So we're going to have 3 times 3 centimeters, which is going to be 9 centimeters as our distance they are apart on the map. And a quick note, if you're carrying your units through your problem, notice how kilometers cancels out with kilometers, and all we're left with is centimeters. So we know that x is going to be centimeters. Let's move on to number 4. Okay, so now we're going to find the distance between Riverside and Milton if they are 12 centimeters apart on a map, but this time we're using a map with a slightly different scale. The scale on our new map is 4 centimeters to 21 kilometers. So if we know our scale is 4 centimeters to that 21 kilometers, we're going to try to find how far apart they are if they're 12 centimeters apart on the map. So keeping our centimeters in our numerator, our denominator is going to be our unknown. So what's the actual distance between those two towns or cities? So we're going to have to solve for x, which is going to require a little bit more than a one-step equation, or to make this easier, I can just rewrite this proportion. Let's flip our fractions around. So we're going to write 21 kilometers over 4 centimeters is equal to our unknown x over 12 centimeters. So you can see that my centimeters are now in my denominator, whereas my kilometers are going to be in my numerator. One-step equation, multiply both sides by 12 centimeters. Notice 12 centimeters cancels out on my right-hand side, and centimeters will cancel out on my left-hand side, so I'm going to be left with kilometers. But what exactly is that value? Well, 12 times 21 divided by 4, it's going to be easier if we do 12 divided by 4 first, which is 3, and 3 times 21 is going to be 63. So 63 kilometers is the distance between Riverside and Milton. That is our x, which is our unknown for this proportion. Moving on to number 5, it says that a model house is 12 centimeters wide. If it was built with a scale of 3 centimeters to 4 meters, then how wide is the real house? So how wide is the real house if we know it's 12 centimeters? So that's going to be our unknown x, or if you want to, just to show you that a variable is just going to represent some number, this time let's make our variable a. So a is how wide the real house is, and the model house itself is 12 centimeters. So now we're going to set this proportion up, or this ratio up, with our scale, 3 centimeters to 4 meters. Centimeters is in our denominator, so I'm going to put my 4 meters in my numerator over my 3 centimeters. Now, one-step equation. Multiply both sides by the 12 centimeters. When we multiply both sides by that 12 centimeters, we'll isolate our variable a. So we're going to get that a is equal to 12 times 4 over 3, which is going to leave us with 4 times 4, which is 16. And notice that my centimeters gets canceled out, so that's 16 meters. So the actual house is 16 meters long. Moving on to number 6, it says that Oak Grove and Salem are 87 miles from each other. How far apart would the cities be on a map that has a scale of 5 inches to 29 miles? So if we know that those two towns or those two cities are 87 miles apart, how do you think we're going to set this up? Because what we're looking for is how far apart they are on the map, which the distances on the map is represented by inches. So what I'm going to do is I'm going to write my scale of 5 inches to 29 miles. And that's going to be equal to our unknown. This time let's use some variable c. So 5 inches over 29 miles is equal to some distance c over the 87 miles those cities are actually apart. Again, one-step equation. Multiply both sides by 87 miles. When we do this, notice that the miles gets canceled out, so we're left with inches on our left-hand side. So c is just going to be equal to 87 times 5 divided by 29. And actually, 29 goes evenly into 87 3 times. So this is just going to be 3 times 5, which is 15 inches. And if you need help recognizing that 29 goes into 87, what I like to do is try multiplying it by a small number. So if you multiply it by 2, 29 times 2, if you're doing it in your head, you multiply the 2 by the ones place, so that would be an 18. 2 times 2 is 4. 4 plus 1 is 5. So 29 times 2 is 58. So not quite 87. Let me try 29 times 3. 29 times 3, that 9 times 3 is 27. And 87 ends in a 7, so this might be the winner. Carry over our 2. 2 times 3 is 6. Plus 2 is indeed 8. So again, 15 inches is how far Oak Grove and Salem are apart on the map. Let's move on to number 7. Again, for number 7, we're dealing with a map. And this map has a scale of 2 inches to 6 miles. And if Clayton and Centerville are 10 inches apart on the map, how far apart are the cities in real life? To keep this as a one-step equation, if we know both sets of inches on the map, the one for the scale and the one for how far apart the cities are, what we're trying to solve for is how far apart the real cities are in miles. So this time, just to mix up the ratios a bit, as opposed to keeping my scale within my same fraction, I'm going to keep my inches within my same fraction. So I'm going to say 10 inches over 2 inches is going to be equivalent to how far apart those cities are, x over 6 miles. Now note, here is my scale down here, and here is what represents those cities. So my denominator is now my scale, and my numerators are how far apart my cities are. So 10 inches over 2 inches, we can simplify this down before we even multiply by 6. 10 inches divided by 2 inches is simply 5, and that's equal to x over 6 miles. Now you'll see that when I multiply by 6 miles, we're going to get a total of 30 miles. So those cities in real life are 30 miles apart. Now the last one for this set of instructions, number 8. And for number 8, I think a picture is going to be helpful because again, it's setting up shadows and lengths of figures, which I think pictures are always helpful for. And before we actually do this, if you're finding this video helpful, feel free to click that like button and subscribe to my channel so that you're updated when I come out with new videos. But moving on to number 8, we have a statue that's 12 feet tall. So I'll go ahead and draw a statue, and I'll make my statue a person. So this statue is 12 feet tall, and it casts a shadow that is 15 feet long. And now we're going to find the length of a shadow. So some length is what we're searching for. Let's write this as variable x. That an 8-foot cardboard box casts. So I'm going to draw my 8-foot cardboard box. Now, all we need to do is set up these proportions. So I'm going to have the length of my shadow of my statue over the height of the statue itself, 15 feet over 12 feet, and that's going to be equivalent to the length of my shadow of my cardboard box, x, over the height of that cardboard box, 8 feet. Now, one thing I can do is multiply both sides by 8 feet. And when I do so, I'm also going to simplify this fraction down because it's going to make my life a little bit easier. I know that both 15 and 12 are divisible by 3, so 15 feet over 12 feet is really going to be 5/4. 15 divided by 3 is 5, and 12 divided by 3 is 4, and that's all equal to x. Now, look, I have 8 divided by 4, which is 2, and 2 feet times 5 is 10 feet. So 10 feet is equal to x, and remember that x represented the length of my shadow of my box. So 10 feet is that length. Now in our next 4 problems, numbers 9 through 12, we're going to answer each question and we're going to round our answer to the nearest tenth. So same exact way we've been doing up above, except now we're going to be working with some decimals. For number 9, it says a model house has a scale of 1 inch to 2 feet. If the real house is 26 feet wide, then how wide is this model house? Well, we're looking for how wide the model house is, so that's going to be that measurement in inches. So we're going to have 1 inch over 2 feet. There's our scale, and that's equal to some variable. Let's use the variable h for house over 26 feet. One-step equation, I'm just going to multiply both sides by 26 feet. And the nice thing about this problem is, look at that numerator. That numerator is 1. So I'm going to have 1 times 26, which is 26. So all I'm doing is 26 divided by 2, which is going to give me 13. And notice, that's going to be 13 inches. So 13 inches is equal to h. And remember, our variable h is how wide that model house actually is. So 13 inches is our solution for number 9. So we didn't even have to deal with decimals in number 9, but I have a feeling we are going to in number 10. Looking at number 10, it says a 6.5 foot tall car standing next to an adult elephant casts a shadow that is 33.2 feet. So I'm going to go ahead and draw some car. Let's see these drawing skills. Well, I know it's 6.5 feet for the height, so I'll start with that. And let's see if I can draw this. We'll put the wheels, the body. There we go. There's my car, and it casts a shadow that is 33.2 feet long. If the adult elephant casts a shadow that is 51.5 feet long, how tall is the adult elephant? So our adult elephant, variable x, that's our unknown. We don't know how tall this elephant is. But we do know that it casts a 51.5 foot shadow. So think about it. If the shadow of the elephant is a lot longer than the shadow of the car, what do you think the elephant's height is going to be compared to the car itself? It's going to be bigger. This is going to be bigger than 6.5 feet because its shadow is longer. So let's go ahead and set up these proportions. We'll do 6.5 feet, that's the height of the car, over the length of its shadow, which is 33.2 feet, and that's going to be equal to some x, which is our height of our elephant, over how long that shadow is, 51.5 feet. What we can do is one-step equation. Multiply by 51.5 feet to both sides. Now feel free to use a calculator, or if you can't, multiply and then do some long division. But 51.5 feet times 6.5 feet is going to be 334.75 feet. And if I divide that then by my 33.2, I'm going to get 10.08. But remember, if this number, without any rounding, is 10.0828 and so on, we're rounding to the nearest 10th. So I'm rounding to this place here, and if I have an 8 next to it, this is going to get rounded up to a 1. So this is going to be 10.1 feet. So the elephant has a height of 10.1 feet. Let's move on to number 11. All right, so for number 11, again, I think a picture is going to be useful. If we have a 42.9 foot tall flagpole that casts a 253.1 foot long shadow. So here we go. Here's my flagpole. It has a height of 42.9 feet. And it casts a 253.1 foot long shadow. So 253.1. And let's go ahead and make this flag pretty colorful. So we're going to try to figure out how long is the shadow that a 6.2 foot tall woman casts. So we know the height of the flagpole, the length of its shadow, we know the height of a woman. So how long is her shadow? That is our unknown. And let's make this unknown A. So if we're solving for A, we're going to have to set up some proportions. And remember, it's easier if we keep our unknown in our numerator, so it's a one-step equation. So I'm going to say that A over 6.2 feet is equal to 253.1 feet over the height of that flagpole, 42.9 feet. Solving for our unknown A, one-step equation. Multiply both sides by 6.2 feet. When we do that, we'll get that the height of the woman A is equal to, on a calculator, go ahead, pull it up, and type it in. 253.1, multiply that by 6.2, and then divide that answer by 42.9. When we do so, we're going to get a number that's 36.5785, and so on. But remember, we're rounding to that nearest 10th. Next to that is a 7, so this 5 is going to round up to a 6. So 36.6 feet. That is the length of the shadow that the woman casts. Now, on to our very last problem, number 12. And we're back to dealing with maps. So it says that Georgetown and Franklin are 9.7 inches apart on a map that has a scale of 1.1 inches to 15 miles. So we know how far apart they are on the map, and we know the scale of that map. So how far apart are the real cities? That measurement is going to be in miles. So I'm going to write my 9.7 inches that the cities are apart, and I'm going to put my scales in my denominator. So inches and inches, that'll be 1.1 inches in that denominator, and I'll have 15 miles in this denominator. There's my scale, and my unknown distance the cities are apart, we'll call that variable C. One-step equation, multiply both sides by 15 miles. 15 miles cancels out with 15 miles, so I'll get that C is equal to, inches cancels out with inches. I know that my units is miles on this left-hand side, so I'll do 15 times 9.7, which is 145.5, and I'm going to divide that by 1.1, which is going to be 132.27 repeating. Rounding to that nearest 10th, if I have 0.27, that 2 is going to go up to a 3. So I'll have 132.3 miles. That's how far apart Georgetown and Franklin are. And with that, we wrap up this worksheet. If you have any questions, please feel free to leave them in the comments below. And as always, don't forget to like, subscribe, and share.